In this video, we are going to discuss about transformer on no load. In the previous video, we discussed about the ideal transformer and its phasor diagram. Basically, what is an ideal transformer? An ideal transformer is that which is having no core loss, no copper loss. Here we are going to consider a practical transformer or the actual transformer. Suppose this is the symbolic representation of a transformer. This one is the primary winding and this one is the secondary winding. Why it is primary winding? Because here in this winding the AC voltage source is connected. This V1 is given as Vm sine omega t. This primary winding, this one is the secondary winding. When it is said that transformer on no load, it means the secondary winding is kept open. Here it is kept open. Now when the primary is connected to the AC supply, what will happen? There is a flow of current I, and this I is given as I naught, and this I naught is known as no load current. This no load current will start flowing into the primary winding of a transformer and then back to the supply. So here I naught is what? It is a no load primary current. When the transformer is on no load and it is the primary is connected to the AC supply, what will happen? It will produce two losses. One is copper loss, one is core loss, and the other is copper loss. Okay, so what will happen? This I naught, when it flows into the primary winding, so the flow will be V1. When voltage V1 is applied to the primary winding, there is a flow of current I naught, and because of this I naught, when it flows into the winding, it set up a flux phi, and this phi links with the primary winding and produces an EMF which is known as self-induced EMF E1, which opposes the applied voltage V1 as per Lenz's law. So V1, then I naught produces a setup flux phi, and because of this flux phi, there is a self-induced EMF E1. Okay, and when this phi is linked with the secondary winding of a transformer, what will happen? It produces a mutual induction. Because of the mutual induction, it produces another EMF in the secondary winding, which is given as E2. This is what E2 is. What it is? Secondary EMF or the secondary induced EMF voltage. This is what E2. As this terminal is kept open, it means there is a flow of current which is I2 is equal to 0. Why it is 0? Because it is an open circuit, the current will not flow, and the terminal voltage V2 is equal to E2. It means V2 is equal to E2. Okay, now suppose this transformer is connected, a wattmeter is connected to the primary winding of a transformer. What will happen? This wattmeter W1 will measure or gives the reading of input power at no load condition. It means W1 is going to read V1, then there is a flow of current I naught, no load current I naught dot cos phi naught, where V1 is what? It is a applied voltage, I naught is no load current, and cos phi naught is what? It is a no load power factor of a transformer. So it means what? This W1 wattmeter reads the no load input power. Okay, this W1, it will show or it will measure two losses. One is core loss and another one is copper loss. It will measure two losses, that is core loss and the copper loss. It means I naught is having two components. One is Im or I mu, known as magnetizing current, and the other component is Iw, known as working current. Okay, this I mu is responsible for producing core loss, whereas this Iw is responsible for producing copper loss. It means I naught is what? I naught, no load current, has two components, that is Im and Iw. Okay, so now if we consider this primary circuit as purely inductive, means we are not considering resistance. What we are considering it is a purely inductive. Then what would be the phasor diagram? If primary winding is purely inductive, it means this is what? This is V1. It is on x-axis, and the current will lag by an angle 90 degree, isn't it, when it is purely inductive. Okay, this I naught is responsible or set up of flux phi, which is in same phase. This is what phi, and this is phi naught, no load power factor angle. Sorry, this is not the no load power factor angle. This is what phi, flux. Okay, so this is for purely inductive circuit, but right now we are considering the practical transformer. It means this phasor will become like this. This is what V1, this is phi. As the primary winding is or the transformer is practical, so it will lag by an angle some phi naught. Phi naught is what? It is a no load power factor angle. This is what I naught. Okay, so this is what the practical phasor this is what the phasor diagram for a practical transformer at no load. Now suppose this is on the x-axis. Okay, now suppose we change the orientation or we rotate it by 90 degrees. So what will happen? It will become like this. This is what phi, this is V1, and this is I naught. And phi naught is what? It is an angle between V1 and I naught. So this is phi naught. Okay, now this I naught can be resolved into two components, that is Im and this one is Iw. So resolving into the phasor diagram or the vectors, this is what Im, magnetizing current, which is responsible for producing flux, and this is what Iw, which is on x-axis. This V1 is on x-axis. Okay, and this is on y-axis. Just we have what we have done, we have changed the orientation. Okay, now previously what we had learned, we learned this flow. When there is a V1, there is a production of I naught. Then due to the flow of I naught in the primary winding, there is a setup flux phi, and this setup flux phi will produce E1, which is opposing to this V1. It means E1 and V1 both are in opposite direction. It means this is what E1, and when this flux is mutually coupled with or linked with the secondary winding, it set up another flux, another EMF, that is known as secondary induced EMF E2, which is equal to V2. Suppose it is greater than E1, so this is what E2, and this E2 is equal to V2. So this is what the complete phasor for this practical transformer when it is on no load. Now this Iw is what? Iw is what? It is a working current. This Iw will be given as I naught, if we are resolving into the components, I naught cos phi naught, And similarly Im, or magnetizing current, or in some text it is given as I mu, could be resolved into I naught sine phi naught. This is what the basic concept of the resolution of the vectors. Suppose this is a x-axis, this is y-axis. Okay, suppose there is a vector, this is suppose u, and it is making some angle theta from the x-axis, and then if we resolve it into the two components, what will happen? This is what u cos of theta, and this is what u sine of theta. Don't confuse it with that this is the y-axis. This is the x-axis. So on the x-axis there is a cos theta component, so IW is on x-axis, so this is a cos theta component, whereas IM is on y-axis, so IM is what? It is sine naught. So we can say that I naught is equal to under root IM whole square plus IW whole square. It is what? It is a right angle triangle. Okay, this is what? This is a right angle triangle. This is IM, and this phasor is equal to this much. This is what, or we can say this is IW, or this IM is equal to this phasor. So this is what, this is making an right angle triangle. Okay, so on the basis of that, by using Pythagoras theorem, we can write I naught is equal to Im whole square plus IW whole square, which is what the resultant current I naught. Okay, thank you. This loss, or the W1, this is what the wattmeter reading. It is measuring two losses, that is copper loss and core loss. Further, this core loss is divided into two. One is hysteresis loss and the other is eddy current loss. Okay, one is what? Hysteresis loss, the other is what? It is a copper loss, and eddy current loss. This copper loss depends upon the resistance winding, or the winding of a resistance. So here in this W1, it is measuring two things, that is copper loss and core loss. So copper loss and core loss. This copper loss, because it is a no load condition, this copper loss is very small. So this, as it is a very small, it can be negligible. So it means only the significant loss is what? It is a core loss. It means when transformer is at no load condition, it, or we connected a wattmeter, measures the core losses. Okay, when the transformer is on no load condition, it measures core losses. Therefore, we can conclude that what is the significance, what is the necessary to study transformer at no load? To study transformer at no load, we can find out the core losses produced in the transformer. Okay, thank you.